Welcome to The Explainer. I am absolutely thrilled to have you here today. Look, if you're a focused learner, prepping for a major quantum information theory exam, or honestly just someone fascinated by the hidden rules of reality, you are in exactly the right place. Today, we're relying strictly on clean, abstract dimensional schematics. No generic sci-fi glowing orbs, no Hollywood magic, just the pure, elegant logic and structure of the quantum universe. So, let's jump right in.
Now, this is the number one question on quantum exams, and it's the exact mystery we are solving today. Why does the universe absolutely fundamentally forbid you from hitting copy and paste on a quantum state? In our daily lives, copying data is trivial, right? You just duplicate a file. But in the quantum realm, trying to duplicate information triggers a hard physical boundary. Let's find out exactly why that happens.
Section 1. Establishing the baseline. Bits versus qubits. Okay, moving on. Before we can mathematically prove why copying is impossible, we really need to define the fundamental units of information we're dealing with. The contrast here is stark. Think of a deterministic copper-orange classical bit. It is strictly a 0 or strictly a 1, basically a standard light switch. But a goldenrod yellow quantum qubit, that exists in a superposition of states simultaneously. We read its mathematical formula as the state ket psi equals alpha ket 0 plus beta ket 1. Alpha and beta are complex numbers representing probability amplitudes. It's kind of like a spinning coin, a blur of both states until you actually force it to stop.
Section 2. The mathematical proof, the No-Cloning Theorem. Let's get into the math.
That blurred quantum state brings us to the absolute bedrock of quantum cryptography. And trust me, this is a massive priority for your upcoming exams. The definition of the no-cloning theorem is completely uncompromising. It states that it is physically impossible to create an identical copy of an arbitrary unknown quantum state using any unitary or quantum physical process. And this isn't just a technological hurdle, it is a literal law of physics. This single rule prevents eavesdroppers from silently intercepting quantum crypto signals, and it's the exact reason why quantum computers cannot simply back up their data halfway through a calculation. Okay, I am going to slow down the pacing drastically right here, because this is the mathematical proof you will likely need to write out on test day. Let's just walk through it step by step. Step 1. We assume a universal cloning machine actually exists. It takes an unknown state, let's call it ket psi, and a blank target state, ket 0, and supposedly outputs two perfect copies, ket psi, ket psi. Make sense? Now, step 2. Because quantum mechanics is strictly linear, if we input a superposition state where ket psi equals alpha ket phi plus beta ket chi, the cloning machine's output must distribute linearly. It would output alpha times ket phi plus beta ket chi. But wait, look at step 3. Here is the conflict. A true, perfect cloning machine multiplying the entire superposition by itself would actually give us a long polynomial expansion with cross terms, alpha squared, beta squared, and those middle alpha-beta terms. So the absolute crucial point is this. The linear output and the true cloning output mathematically contradict each other. They are just not equal, unless alpha times beta equals 0. This proves a general linear quantum copier cannot exist, period. Section 3. The loophole, the quantum teleportation protocol. Well, physics is nothing if not clever. We can't copy a state, but can we move it? Let's bring the energy back up because we are about to look at the ultimate workaround to the no-cloning restriction. Let's break this teleportation protocol down step by step. Step 1. Alice and Bob share an entangled pair of qubits, linked by a pulsing violet-magenta entanglement line. Alice also holds a third, completely unknown target qubit she wants to send. Step 2. Alice performs local operations. She applies a CNOT gate, that's a controlled NOT gate, followed by a Hadamard gate on her target qubit. Step 3. She performs a Bell measurement, instantly collapsing her qubits into one of 4 classical outcomes. Notice that her original quantum state is now destroyed. It wasn't copied, it was sacrificed. Step 4. She transmits her 2 measurement results as standard copper-orange classical bits over a regular channel to Bob. And finally, step 5. Bob's correction. This brilliant little table illustrates exactly what Bob does next. See, until he gets Alice's message, his half of the entangled pair is just a random, neutral sphere of noise. But depending on the 2 classical bits he receives, he applies specific conditional gates. If he gets 0, 0, he applies the identity gate, meaning he literally does nothing. If he gets 0, 1, he applies the X gate, which is a bit flip. A 1-0 means a z-gate, or phase flip, and a 1-1 means an x-gate followed by a z-gate. Once he applies the correct gate based on that classical data, his qubit dynamically transforms back into the vibrant goldenrod state, ket psi. The state has actually been teleported.
But here is a massive conceptual trap you have to avoid on your exam. Does teleportation mean faster than light travel? No way. The answer lies in the speed of light limit, c. Because Bob's qubit is utterly useless noise until those two classical bits arrive through a standard speed of light limited channel, quantum teleportation cannot break the speed of light. The entanglement collapse? Yes, that is instant. But the actual information transfer? It is not.
Section 4, Real-World Application, Non-Locality, and BB84. Let's keep moving.
Let's see how this instant collapse translates into a practical, unhackable, real-world application. This is the famous BB84 protocol, and it leverages everything we've talked about today. First, Alice encodes single photons randomly in either a rectilinear or diagonal basis. Bob measures them, randomly switching between those exact same bases. Then, they publicly compare notes and sift out the bits where their bases matched, creating a raw shared key. But here is where the no-cloning theorem comes back to save the day: eavesdropping detection. If an eavesdropper, let's call her Eve, tries to intercept those photons, she is physically forbidden from perfectly copying them. Her very act of measuring them alters their states. This inevitably introduces noticeable errors into Alice and Bob's final key, instantly triggering an alarm that the channel is compromised. It's brilliant.
Section 5, the takeaway, quick exam prep check.
Okay, we've covered a lot of complex ground. It is time to solidify these concepts into a rapid-fire review checklist to make absolutely sure you have the key takeaways locked in. Here is your high-energy recap. First, remember the no-cloning theorem prevents the perfect duplication of unknown quantum states. Write that down. Second, master the teleportation circuit. When you sketch it out on your test, make sure you clearly draw those double-lined paths for the classical bits traveling from Alice to Bob, right alongside the CNOT and Hadamard gates. And third, underline this in red. Instant quantum collapse does not mean instant information transfer. The speed of light always wins.
As you head into your exams, I want to leave you with this final thought. Think about that shared EPR pair we talked about. A shimmering violet-magenta link snapping, instantly determining a parallel reality across the vastness of the entire universe, yet perfectly constrained by the unbreakable rules of classical transmission and the no-cloning limit. The universe is protecting its most fundamental secrets, forcing us to play by a rulebook that is as elegant as it is strict. So keep studying those schematics, keep questioning the rules, and I'll see you on the next explainer.